Okay, hi everyone. It's good to see you all here. And today we'll talk about seeded extractors. Okay, so what's a seeded extractor? It gets an input, 0, 1 to the M, and a seed, 0, 1 to the D, and outputs. The output from 0, 1 to the M. And what do we want from the extractor? To fool us to think it's uniform. Yeah, we want the output to be close to uniform. Okay, we want the extractor X with a seed is approximately uniform on n bits. So I need to say what X and S.
And this is X source and this is.
Yes, so for every K source X, so this should be. Can you switch markers? What? Can you switch the back? For every K source X, the output of the extractor over a sample from X and a uniform seed is close to uniform. And what does this symbol mean? Statistical distance. And so can be written as a thing to have the norm 1 of the extractor minus the uniform distribution. Okay, so this is X and S, and this is just uniform. When we look at the extractor and the uniform distribution as a vector with all possible outputs, so the uniform distribution is just 1 over 2 to the M, and this is the probability. Okay, so today we're going to construct the seeded extractor based on random walks and expanders. Let's just say what's K source. So it means that the mean entropy of X is post A, which means
No, you wrote it correctly. You said it correctly.
Yes. Okay. And what does this mean? It means minimum over 1 over log 1 over probability of X. X in suppose. Right? Familiar? Yes, familiar. And in particular, it means that X is distributed over at least 2 to the K elements, right? So, in other words, probability of X equals X is at most 2 to the X. Okay, now let's construct the. Let's say which parameters are the best. Write it there. So for a K epsilon extractor, we have the optimal values of S, the seed length equals log n minus K plus log 1 over epsilon. And for M, so what should M be?
N plus 3, K plus 3.
K plus,
and then you've got the log of
K plus S actually,
S.
because you can think of it as the number of random bits that we had before, right? K, the X had K random bits, and we used the
Switched.
right. Sorry. And
It was, I think it was log of 1 over
minus
minus
log.
yeah. Yeah, this was the here minus that. Yes.
Okay, we are not going to get close to these parameters today, but we're going to do something. And we'll start describing the construction. So we'll have an expander graph. Call it G, and it's an omega expander. And it has degree D equals 2 to the D. And it has 2 to the n vertices. We get an input x. What are we going to do? What we always do in expanders, random walk. Okay, so we interpret x as one of the vertices, and then we use the seed in order to choose where to step. Okay, so S is going to be B times T, where T is the number of steps we are going to perform, and D is the number of bits that we need for an instruction for each step. Okay, and then we just take a random walk, and it ends in a vertex Y, and we return Y. Okay, so extract of X with the seed S is Y. And now we need to prove that this is a good example. And let me start with the high-level analysis of what we expect the parameters to be. Okay, so if X is a K source, we can think of it as a flat source, and it must be distributed over 2 to the K elements, right? So we have X somewhere 2 to the K elements out of 2 to the K. Now, in each step, we are going to see at most D, capital D, new neighbors. So we're going to need at least, so after one step, we're going to have K plus D, and then plus 2D in the second step. So in order to see every vertex, we're going to need K plus D equals A, right? So we're going to need, and this is S. So S is going to be n minus K, at least n minus K.
T is just some parameter.
T, yes, we're going to fix it later. It's the number of steps in the random. Okay, but you see that the number, the size of the seed is going to be n minus K, which is not even close to the optimal, which is log n minus. Okay, so it's not a very good extractor, but it is something. Okay, and let's move to the analysis. Extractor, so we're going to analyze norm of extractor. It's norm 1. So norm 1 and expanders don't work well together. So we'll move to norm 2, the norms inequality. So it's square root n, capital N is 2 to the n, times the 2 norms. Okay. And now for this one, let's write this as so it can be written as x times W to the T. Here. Right? Because you start with the initial distribution on the vertices, which is induced by X, and then you take T random steps, and you finish with another vector. And how can I write this one?
You can also do W to the T.
Yeah, W to the T times U times the all ones vector. And let's keep everything normalized. So we have 1 over n, which coordinates. Okay, what now?
Take out.
Just the multiplicative.
X minus n.
Now multiplicative with norm, like it's bounded by the norm of the W to the T and the norm of Z.
Okay, but what is the norm of W to T?
One. Not one, on the omega to the T.
No, it's not. No. It's
Because
one.
I do have the one.
So it's
Yeah, so we're not going to do that.
yeah.
Not going to do this.
Somehow mix them. Somehow.
Yeah, okay, all we need to know is that this one is perpendicular to the all one.
Yes. So this is the norm.
Yes, so the norm of this one is at most omega to the T times the norm of, so even though the norm of W is 1, we live in the perpendicular to the all ones vector, and we get the factor of omega to the T. Norm of X minus 1. Okay, so now we need to analyze this one. It's
Because
yeah, so X is a distribution. It's
Oh,
it's this sum is 1, and this one also. Okay, so X minus 1 to the n. And 1 over n. So let's compute the norm squared. So it's like the norm of X plus the norm 1 minus 2 times X transpose times 1.
and square is
Yeah.
square.
Okay, let's start with this one. It's easy.
and no, it's normalized.
1 over n, right? And entries, each one is 1 over n squared. This is just 1 over n. How about this one?
1. Yeah.
It's
Distribution. Oh, it's a 1 over n.
right because this adds up to 1. Multiplying by the all ones vector and just summing everything. So minus 2 over n. And this is the only interesting part left. And so now we're going to use the fact that X is a K source.
So it's bounded by the max.
Yeah, so what's written here?
It's flat source against.
No.
We don't need to assume this.
Because it's because we have the property of it's in entropy, we can use that for bound.
Yeah, so we write it as so norm of X squared with the sum of probability X equals X squared.
Is it close to one?
At most
To be in.
max of the probability X equals X and some probability of X equals X. Well, let's call it X equals Y. This is
The max case is 1.
what?
So the max case is 1.
A times first. Right? So this is just a trick.
No,
Let's take things. Okay, so let's roll everything back. So we had the one norm bounded by square root n. So the x minus q no 1 is a closed square root n times omega to the t from here times the norm. This, which is the norm squared, so we need to take the square root. So times n to the minus k over.
It's minus 1 over n.
Minus 1 over n. Minus 1 over square root of square root of
Minus 2.
no, that's
No, just 1 over.
But you have square root of that's there you have 1 over n minus 2.
Okay, so
It's to the minus k and then square root of
this is very small, right?
Yeah.
So let's just ignore it. It's much smaller than.
But it's not, and the roots everything, so.
Yeah, but they already
Everybody
resolved
needs
into
that.
the k over 2.
Okay.
Yeah, okay, just to. I think we need this. Right, so this is at most 2 times this. The 2 absorbs all the arrows with the minus sign that we have. We think it's okay.
What? No.
Yeah.
No, the other way around. Like we got it without the 2, and then we added. So it's not.
So do you agree with the inequality on the board?
No.
So,
Now it's right, kind of.
yeah, okay, so let me add it too. It's not going to matter. It's just to make sure all the tiny elements. Okay, so this is the error of the extractor, right? Yes, so now let's work out the parameters. Okay, so omega equals 1 over square root order. Okay, because this is the best expander you can expect. And d is so 2 to the minus d over 2, right? Most 2 times 2 to the d over 2 times d minus, wait, why is this? My omega 1 over square root. Oh, bigger, okay. Times 2 to the minus k over 2 times 2 to the n over 2. This one. No, 2 times 2. So we have
n minus k minus dt over all of this.
and we need this to be small. We need this to be equal x. So we need to choose. Okay, let me ignore this too. So n minus k minus dt equals log 1 over epsilon. Plus,
Yeah, two. Using 2 because it's divided by half in the exponent.
2.
The y 1 over.
And yeah, there's no one.
No, it's epsilon.
It should be epsilon. Right?
Because afterwards we're gonna work with the big T. It's okay.
You're gonna get a plus log of epsilon or minus log one.
You can switch all the pluses and minuses, and then
It's okay. We work with epsilon is the 1 over. It's here. It's log epsilon.
Okay, first of all, let's call this one S. So it would be like my And now we have, let's call this one. Plus one. And now let's take the inverse, so we'll have log 1 over epsilon.
Why would you?
Just
Or S.
Log 1 epsilon, and here we take the inverse, so we
K
have
plus S minus N.
K plus S minus N.
Well, all that. Over two plus one. Yeah.
Plus 1.
Plus two.
Plus two.
Okay, so we have S equals
MS.
N minus K plus 2 log 1 over epsilon.
Plus constant.
Yeah. Okay, so we call again that the optimal parameters are S equals log N minus K plus 2 log epsilon, 1 over epsilon, and we only got, as we expected, N minus K.
And now we need to show the M or
So what is M in our construction?
mass again.
N. It's the number of bits that we return, and it's just by definition of the extractor, it's just N.
Okay.
This extractor was from end to end, right? Like, and this extractor was from end to end.
End to end, yes. So how is it compared to the optimal in terms of M? So yeah, it's the best, right? Because we have S equals N minus K. So altogether we have N bits. Yeah?
Where's the minuses? Like you said,
Minus the log N minus K is better than N minus K.
It's saying that whatever that's better.
it cannot be better than the optimal. Why do we have something
This is
better?
It's less regarding to M, regarding to S.
But the optimal of M is using S. For every S, this is the optimal M. It's not what we're saying.
I don't think this is I'm not sure this is a lower bound, this is what you achieve.
Oh, that's the probabilities.
Yeah.
Everything.
Like it has like your goal.
Yeah, yeah, I thought it's not.
Maybe there is a lower bound, no.
So Gil always says that you some
S equals N.
some reason you have to lose the 2 log 1 over epsilon factor, but I'm not sure why, and it seems like we don't lose it here, so maybe we are so far from optimal in the seed parameter, so maybe in this parameters regime, this is just possible. Okay, so I have nothing more to tell you. This was all the station.
Wow, that not fast.
Yes. Thank you. Thank you.